Bom, bom dia a todos, sejam todos aí muito bem-vindos a mais um PPGMCS recebe. Eu sou o Murilo, atualmente sou professor externo aqui do programa, e hoje é com muito prazer que a gente vai receber aqui o professor Norbert Tihanyi. Ele é atualmente pesquisador líder no Instituto de Inovação Tecnológica de Abu Dhabi, e ele vai falar para a gente um pouco sobre a aplicação dos grandes modelos de linguagem, né, os LLMs, que estão bastante em voga aí atualmente, especificamente no contexto de segurança de software, né? Então, apresentando rapidamente o professor Tihanyi, né, ele é bacharel e mestre em engenharia de segurança, doutor em tecnologia e ciência da informação pela Universidade Eötvös Loránd, na Hungria. Por mais de 7 anos, o professor serviu como criptoanalista e engenheiro de segurança é, no que se chama da Agência Nacional de Segurança húngara. Ele também representou a Hungria como membro da OTAN e nos subcomitês de garantia de informação da União Europeia. E por 3 anos foi gestor sênior da Ernst Young na área de segurança. Entre 2022 e 2023, liderou o laboratório de criptografia e hardware na Zenith Labs em Abu Dhabi e atualmente é pesquisador líder no Instituto de Inovação Tecnológica em Abu Dhabi também. Desde 2020, ele é membro da Academia Húngara de Ciências e possui diversas certificações internacionais na área de segurança. Então, sem mais delongas, né, gostaria de apresentar o professor Tihanyi. Hello, good afternoon, Professor Tihanyi.
Thank you very much for the invitation. Can you, okay, I didn't share it. Okay, let's share my screen.
Yes, so first of all, thank you very much for you to be here with us today. I'd like to welcome you to our series of seminars where we invite researchers from all around the world to speak about recent advances in computational technology, and it's used to tackle a broad range of subjects from industrial problems to our own development as a society. I just gave a very brief presentation of you in Portuguese right now, but feel free to present yourself in English as well if you like. It's an honor to be with you here today. So I'm gonna pass the microphone to you now, so you can talk about this kind of intriguing subject of large language models and software security.
Thank you very much. Thank you very much. If you introduced me, then I don't want to do the same in English. So thank you very much for the invitation. And I'm going to share my screen. I would like to get some feedback that can you see my screen properly? And also, can you hear me correctly?
Yes, I can see your screen and I can hear you as well.
Okay, thank you very much. So basically, I was working in many different projects regarding to cybersecurity cryptanalysis, and also we are now doing many different projects regarding to large language models and software security and software verification. And this is also a joint work with Lucas Cordeiro, and we had a lot of interesting results regarding with large language models and how to use these kind of models to verify software and try to repair code. Basically, today I want to show you some interesting results that how we generated dataset, and after that how we use these kind of things to repair some code, and after that how we use formal verification methods to find vulnerabilities in the AI generated code, and after that how we train some large language models and generative AI in order to try to fix these codes. Okay, so basically in the first slide, there are some challenges in software verification. Maybe you already know that there are many interesting things in software verification. So the first one, if we want to use and we want to teach for AI, the software verification and software healing, the first step is a large and diverse data set. Basically what we have checked, there are many different data sets, but they are not good to use for data set for AI training. So basically we need to generate a new one. And for this one, I'm going to show you how we did it and what kind of formal verification methods we used to find vulnerabilities on the data set. After the lab classification of the data set, we were able to use some AI to this data set used to train the AI, and after that, we use some software healing to automatically fix the vulnerability in the code. So the first challenge is the large and diverse data set. We don't have such kind of data set. The second one is the deep arithmetic understanding. So basically, it's really hard with large language models and different AIs to understand the arithmetic. The third challenge is vulnerability detection. That, of course, vulnerability detection is really important. Which code is vulnerable, which code is not vulnerable, and maybe as you're familiar with formal verification method, we can verify many different things. However, to teach this to an AI or a large language model, once again, we need a proper data set. And the next challenge is to avoid false negatives and positives. When you are using some method like static analyzer tools, then they can produce a lot of false negatives and false positives. So basically, this is what we want to avoid. And this is the reason why we choose BMC, bounded model checker tools, to find vulnerabilities in code. And if there is a problem with the code, we can be 100% sure that there is a counterexample, there is a problem in the code. And this is the reason why we use these techniques to label our data set to avoid false positive and false negatives. If we have too many false positives or false negatives, then after that, when we try to teach for an AI, then it can be a lot of problem to understand which code is vulnerable and which code is not vulnerable. Of course, there is also real challenges. You have heard about this topic, maybe hallucination, that AI sometimes say that this code is vulnerable or this code is not vulnerable, and basically it's totally uncorrelated. So it means that we have to identify these things. And also for this one, we need a proper data set with appropriate labeling. And for this appropriate labeling, we have used bounded model checker tools. And the last one is, of course, equivalency checking. If we want to fix the problem in the code, for example, we have an original code and we identified some bug in the code. After that, if we want to fix the code, it's a really hard mathematical problem to check the equivalency of the two programs. So basically, the first one is the original program, and the second one is the modified program. If we have to check that these two programs are the same, then it's a hard mathematical problem. So basically, these are the main challenges that we need to focus on and we need to solve. And of course, this is an ongoing research, and this is a really hot topic right now. So basically, it's step by step we try to solve most of the challenges. So the first step is the data set creation. I'm going to show you that what we have done and how we did it. And of course, this kind of methodology can be used with different languages, and it also can be used for other types of methodologies. And basically, what I'm going to show you here, this methodology is really good to create different data sets. So basically, we have generated the Form AI dataset. We call this Form AI. Basically, this is some funny words because it's really like a form AI and formal verification. So basically, this form AI dataset is generated by large language models. It's actually generated by GPT 3.5 Turbo. However, of course, many different large language models exist. Also, TII Technology Innovation Institute introduced Falcon. So basically, many different large language models can be used to generate code. The main question is that the generated code quality is good. The generated code can be compiled, and basically these are the most important research questions when we want to create a data set. So basically, we published a data set which is AI generated and contains more than 100,000 codes. So exactly contains 112,000 compilable and independent C programs. Compilable means that we have checked each and every program that generated by the AI that is compilable. For example, it's really easy to use a Linux system with GCC, and with the compiler, we use some method to check that is the program is compilable or not. And independent means that all of the programs, because there are many different data sets on the internet, that the most problem with these data sets that they are not compilable, and it's really hard to analyze them. So the first step was to generate a large data set, more than 100,000 C code. It's quite good, and we use some dynamic zero-shot prompting technique. And of course, in this data set, there are different programs with different varying level of complexity. So for example, in this data set, you can find some chess program, you can find some encryption, table games, simple user programs, many different programs. And the interesting thing is how we generated all of this with AI. And the first step was to generate this data set. And after that, the second one is try to label all of the C program that it contains a vulnerability or not. For this one, we use the efficient SMT-based bounded model checker, ESBMC. The version number was 7.3. So the quite new one. And basically, after that, we have labeled all of the codes in the dataset. And because of this one, we were able to distinguish which code is vulnerable and which code is not. And of course, it's a really interesting question that when we ask AI, for example, GPT, that please generate for me a C code, that it's compilable and is it contains really a vulnerability or not. The data set is already available. The publication is accepted in the 19th International Conference on Predictive Models and Data Analytics in Software Engineering. This will be published in this December. So the conference will be in 8th of December in San Francisco. And the data set already available in GitHub and also in IEEE Dataport. So basically, if somebody wants to play with this data set with 100,000 C code that generated by AI, one can download it and one can check it. And of course, the data set, it contains also the vulnerability classification, what we have done with ESBMC. Basically, the Form AI dataset comprises three distinct files. The first one is the C samples. Of course, all of the C samples can be downloaded from the dataset. So basically, you have all the C code that is compilable with a normal GCC command. Also, we have the classification file with all of the C program is classified based on ESBMC output. And we created a CSV file for machine learning. If somebody wants to teach an AI what program is vulnerable and which not, then it's possible to use this data set. And also we have another CSV file which is human readable. It means that you can open it in a Excel or some editor without the C samples, because sometimes the C code are large. So basically, you can check which code is vulnerable, which code is not vulnerable. So this is the Form AI dataset. And what we are interested in is the methodology, how we created. And here is a very simple, when I'm saying simple, it's really simple, that the data set generation and the labeling framework is not so complicated. We have some type and style. I'm basically these types and style, I'm going to show you what does it mean. This is to ensure that when we are creating programs, it's different. And basically after we have some prompt, like in the GPT, and we have the LLM module. As you can see, the LLM module right now, we have used GPT 3.5. Of course, you can use Falcon, Bard, or GPT-4. It doesn't matter. We ask to generate a code, the LLM module. And after that, of course, we did it in a Linux system, and we checked with GCC with the appropriate includes and everything, and we checked that the generated code is compilable or not. If the code was not compilable because some syntax error or something like that, then we just throw away and we don't want to store it. However, if the code is compilable, then we are going to put into the Form AI dataset, as you can see in the screen. And in the Form AI dataset, after that, we have a large collection of C programs. After that, we have a BMC module. This is the bonded model checking module, where we are using ESBMC.7. And there are three different output: verification failed, of course, verification successful, or unknown. Unknown means that given the threshold and the given time frame, we were not able to decide that the program contains vulnerability or contains no vulnerability. And basically after that, we created a CSV file with all of the C program with these labels. And of course, these labels not only contains that vulnerable or not, but contains the exact output of the ESBMC. So basically, which line is the vulnerable, which variable is the vulnerable, and what is the exact vulnerable. So basically, we have the vulnerable type, so like buffer overflow or null pointer dereference or something like that. Also, we have the line number, and also we have the function name. And based on this, all of this information stored in a CSV file with the original C code. And if somebody is downloading this data set, immediately can see that which program is vulnerable and which program is not vulnerable. And here is how we did it, because I think it's important to speak about that, how we ensure diversity in the data set. So for example, the type means that we have some 200 different options. Basically, in each epic-core randomly chooses a type from 200 options in the type category, including topics like wireless signal strength analyzer, QR code, encryption, table game, password management, or many different programs. This is the type. And we have a style, for example, creative, funny, scientific, multi-threaded. So basically, we randomly choose a type and randomly choose a style, and you can see the prompt, what we have used to generate a C code. The type and the style, because they are random and different, this ensures that we try to create different C programs. For example, as you can see in the slide, write a unique C sorting example program in multi-threaded style. And it's really important to emphasize that we have more instruction in the prompt in order because without this instruction, most of the cases, the code is not compilable. So basically, we needed to add some more things in the prompt. These are the most important things that we have added to the prompt. These are the 5 most important things. So the first one is minimum 50 lines. We don't want to create C programs that are so small. This encourages the LLM to avoid the generation of overly simplistic code. Of course, it's really straightforward. The next one is interesting, but it's important. The be creative. The purpose of this instruction is to generate a more diverse data set. So basically, when we say be creative, that we observe that many different type of C programs are created by the LLM. And of course, as you maybe also observed in many different language models, that sometimes they mention that I cannot create such a C code because it's too complicated. I cannot create the code because it's too long or something like that. And we explicitly instructed the prompt, the AI model, that do not say I'm sorry. This objective is to instruction is to avoid the response that the AI that he cannot do this code or cannot generate the code. And of course, the number 4 in these slides, it looks nothing. However, make sure the program compiles. It's really important. So without this one, sometimes the generation missing some very important header files like stdio or file headers or some like the math header and many different headers were missing from the C program. And when we tried to compile with GCC, it was not possible to compile correctly. So this is really important to make program compilable. And the last one looks silly. However, it also was important that try to start the program with some snippets. After that, it's really easy, that C code extraction. So basically, if we didn't explicitly say something like that, in many cases, the created programs were not compilable because there was some comment, there was some other things that was not belongs to the C code. So basically, when we are starting the C code with these kind of special characters, as you can see in the line number 5, then it means that it's really easy to extract the exact C code from the output. And of course, if we want to automate the code repair and we want to automate the code generation, then we need to do this properly. And basically, in this screen, you can see that the first line, in the first you can see that here is the form AI, the second one is the SARD, and the third one is the big wall. These are all of these data sets. They are not created by AI, they are from real projects. So in the first column form AI, you can see this is generated by AI. This is our data set, and we just check all of the keyword that it can be found in C programs. In C programs, we have 32 different keywords, like if, return, for, struct, as, break, case, as you can see. And the question was that if the generated programs are totally deviating from real life databases, from real life projects, then it means that the generation method is not good because it's not mimic the original projects. And as we can see here, for example, almost in every cases, we have the same number of else, we have the same number of break, we have the same number of if then else, and so on and so on. So it was really important to make this comparison, that to be sure that the created data set is diverse enough. And the next one that I want to introduce, but most of them maybe are already familiar with the formal method checking and bounded model checking. What we have done when we generated all this 100,000 C code, after that, we want to check with bounded model checkers to contains vulnerability or not. So basically, here in this slide, you can see the bounded model checking definition, what is the BMC formula, and basically we are checking that this BMC in aggregation number 1 is satisfiable or not. And if it's violated within case steps, then it means we have a counterexample. This is the formal verification method. This is basically the mathematical definition of BMC models tools like ESBMC. And maybe you're familiar with this one, so I don't want to go into details. But what is really important for us, we have used the ESBMC tool to classify every program which is vulnerable and which is not. Basically, for all of the 112,000 samples, we divided for main categories, 4 main categories. The first one, when the verification was successful, we called VS, and the second one is VF, when the verification was failed. TO, the verification process was not completed, so basically timeout. And then the fourth one is the error. The verification status resulted in an error. For example, the program is crashed or something like that. And these four main categories are really important for us, but the most important is the second one, when the verification status failed. So we need to understand what was the main reason. And with ESBMC, we created 9 subcategories for verification failed: arithmetic overflow, buffer overflow, scanf, fscanf, array bonds violated, the reference failure, null pointer, forgotten memory, invalid pointer, array points violated, division by 0, and of course other vulnerabilities. Other vulnerabilities, any other things that it cannot be classified into the other 8 categories. So these are really important to know. If, for example, we have an ESBMC output, we immediately know that we have an arithmetic overflow or not. And of course, it's very important to emphasize what is the difference between the parameters. And the question is that what kind of parameters we should use when we run the ESBMC. For example, here is the unwin parameter. What is the best way that to put the unwin parameter so high, or what should be the timeout? So basically, with huge computing power, we tested different parameters. K induction, it for example is the K induction. It's also important. Should we use K induction or not, or should we use more time for one program? And as you can see, the winner was the 130 in this line, which is highlighted. And you can see that it means we have used with the unwin parameter, we set the unwin parameter to 1, and we set the timeout parameters to 30. It means that after 30 seconds, if the program was not executed by the ESBMC module, then we just dropped it. So basically, you can see that the running time was 30 minutes. And of course, it's really important to emphasize that these classification results, this is not for the whole 100,000 data set, but it's for 1,000 sample. So basically, we randomly choose 1,000 sample from the data set. And after that, we try to run with different parameters. You can see, for example, the first line in this table, we set the unwin parameter to 2, and we set the timer to 1,000. Basically, it means that the running time was 700, more than 700 minutes. And you can see the identified vulnerabilities on these programs was 2,400. And of course, if we check that the unwin parameter is 1, and we set the timer to 30 seconds, after that, the vulnerable parameter is 2,100. So basically, a little bit more than 2,000. It means that if you see, of course, the first line identified much more vulnerability, 2,400, compared to the 2,100. However, you can see the running time was 700 minutes, 758, and the last one is only 30 minutes. So basically, the time and the identified vulnerabilities, we need to do some compromisation. So basically, the most appropriate parameter based on this small research was to set the unwin to 1 and the timeout to 30. Basically, these are the parameters, and of course, we didn't use K induction. These are different parameters for the ESBMC module, and of course, we wanted to find the most vulnerable functions and lines and codes in the whole FormAI dataset. So basically, we choose these parameters, and all of these parameters were applied for the whole dataset, for the 100,000 samples, because this small classification was tested only in 1,000 samples. The reason was that we did it to find the best parameters. After that, in the whole For AI dataset, we identified more than 88,000 vulnerabilities regarding to buffer overflow, and all of this buffer overflow is associated with CVE numbers. These CVE numbers, it means if you know what is CVE numbers, this is some classification of vulnerabilities. So basically, this is buffer overflow, buffer overwrite, buffer overread, and many such kind of vulnerabilities. As you can see, one of the most frequent is the buffer overflow vulnerability. DFN vulnerability, DFA, if you remember here, DFN difference failure, null pointer, and for example, DFA difference failure, array bounds violated. It means that we have some array and the bounds are violated in the C codes. So basically, it means that we have identified a lot of vulnerabilities in the GPT-generated codes. And this was the first step. This was the generation, and this was the classification of the programs. And what kind of research question we have answered? You can see that research questions, for example, ERC1, how likely is purely LLM-generated code to contain vulnerabilities? And as you can see, more than 50% of the samples from the 112,000 C programs contain vulnerabilities. So basically, it means that GPT 3.5 often produces vulnerable code. Of course, this is not a surprising result because all of these large language models are trained on code written by human beings. So basically, if you go to GitHub, if you go to the internet, you will find the same vulnerabilities because the human being also do the same problems, introducing the same problems in the code. So if we are training a model on codes that is written by human being, then it's not surprise that the GPT is going to do the same problems. And what are the most typical vulnerabilities in LLMs? For GPT 3.5, you have arithmetic overflow, array bounds violation, and buffer overflow. So basically, we have found that when you ask GPT to generate some code, most of the cases, they do arithmetic overflow problem and array bounds violation. This was the first step. We have this data set, and you can also download it, and all of the C programs are labeled that is vulnerable or not. The second one is we want to teach an AI that also to how to distinguish vulnerable code, and also we want to use this for repair some code. So the next step is software healing code repair, how to use this data set for code repair. Let's imagine and let's try to understand the motivation behind this. As you can see, what is the problem with this code? Small vulnerable C++ code. And if you ask some GPT or some large language model, what's the problem with this code? Of course, not every time, but most of the cases, they cannot identify the code because they cannot handle arithmetic operation properly. For example, the LLM answer is there is no problem with this code. The code correctly calculates the value of z and the square of y, and then calculates the value of r. However, maybe you can already see that we have an integer overflow on multiplication in line number 4. In the z variable, when we calculate the y multiplied by y, it means that we will have an integer overflow. However, it's really easy to find by ESBMC, for example, this one, of course, or any bounded model checker. What is the output of ESBMC, for example, for this code? Immediately spot that in line number 4, we have an arithmetic overflow on multiplication in the variable y. And basically, it's really interesting because if we have this information, for all of the 100,000 C program, we store this information in the CSV file. And we can create a new prompt, and we can say to GPT or any large language model that try to fix this code based on the following property. And this property that we get from the ESBMC, we give it to the large language model. Basically, after that, we ask to try to fix the code. And if we give the property violation, because the exact line number, the exact variable name is given to the large language model, the large language model immediately realize what is the problem. So, for example, after that, we have immediately this result and this response from the LLM that, yeah, there is an integer overflow in the Z variable. And when we ask to please come up with a new code, he immediately create a new one. This one you can see in my slide is generated by GPT 3.5 based on the ESBMC output. And the newly generated code is using not a normal integer, but a long int. So basically, this code is not affected an arithmetic overflow anymore. Of course, if we run the ESBMC once again for this code, the verification successful. So basically, there is no any identified problem with this code, and the verification was successful. And this is the idea. If we give the output of the ESBMC to the large language model, then there is a high chance that the large language models understand this, and basically the large language model, there is a chance that can fix the code. In this, you can see how does it work. So here is the first step, the vulnerable C code. You can see this in the first. This is the sample code that I used. And we check with ESBMC model checker, and the ESBMC verification unsuccessful. That it means that we have some problem with this code. And of course, ESBMC give the output, what's the problem with this code. In line number 4, we have a problem on the multiplication. And give this prompt to the LLM, please fix this code based on this. And we give the original source code, and we give this property violation to the large language model. This is the second step. And the third step, in the third step, we try to ask the LLM model to create a new code. And when the new code is created, based on the ESBMC output, we check again the created code that the ESBMC should verify or not. So basically, the output is verified again by ESBMC, and if the verification is successful, sorry, then it means that we come up with a new code that is not vulnerable anymore. And basically, this is the whole idea. And this is the second example. This is also, here is a small C code with like a function name with MD5. If somebody asks, for example, GPT-4, what is the problem with this code, then you see immediately that the GPT will say that, for example, you shouldn't use MD5 because it's cryptographically not secure. Of course, this is not the MD5 function. I'm just use the same name for a normal arithmetic function. And of course, if you use ESBMC, the model, ESBMC checker immediately say verification unsuccessful because he immediately spot that there is some problem in line number 5 in the MD5 function. There is an arithmetic overflow on the multiplication once again. Of course, after that, based on this prompt, we ask the LLM to create a new code based on this property violation. And after that, we check again with ESBMC that the verification is successful or not. And you can see this everything can be automated. And basically to test this, we created 100,000 C code. This is the Form AI dataset, and we can test it with ESBMC, and we can test it with any large language model that the large language model is able to fix the code or not. Basically, this is the methodology. What we are doing, we have a user, we have the original source code. Right now we are using C and C++. We have the BMC module. The BMC module is the ESBMC. And if the verification is successful, then we are ready. If there is a property violation, then we give the original code with the property violation to the large language model to try to fix that code. The large language model came up with a new modified code, and the new modified code is verified again with the BMC module. And if the verification is successful, we are ready. If not, we start again. And you can see there is a loop. And we have identified that most of the cases in 3 or 4 iteration, most of the cases, all of the code were fixed. So this is really promising. And it seems that using some external tool some bounded model checker, and we give the output of the bounded model checker to the modified property violation, and with every information that is needed to understand for the LLM, it seems that the LLM can create a new and secure code based on this property violation. We cannot say that it's always can come up with a new code, or maybe the new code is different from the original one. Of course, it can happen, but based on the research, more than 80% of the cases, we were able to fix the code. And this is a really huge achievement. Basically, for example, we also checked by manually. We selected 20 samples of C codes manually in order to check that the new and modified code is the same. And we check manually. Human beings are verified that the new function and the problem is really fixed. And after that, if the ESBMC tells that the verification is successful, we checked also manually that it's really successful or not. And we can confirm that when ESBMC says verification successful, the new code and the original code were the same. Were the same, it means they have the same behavior. Of course, the vulnerability is fixed. And the last step is in this process, there's machine learning training on Form AI dataset. The Form AI dataset is really interesting. And can we teach, for example, the ESBMC behavior for a large language model? And here is some interesting research. Sorry. So basically, we use Falcon LLM. We fine-tuned the Falcon. Falcon LLM is developed by Tihanyi. It can be found in Hugging Face, and it's free of charge, and everybody can download it, and everybody can play with Falcon. And after fine-tuning, we have the fine-tuned Falcon. And after that, we have the label dataset. This is the label dataset, the Form AI dataset. We split the dataset as usual in artificial intelligence training, the training dataset and the test dataset. And basically, the training process is based on the fine-tuned Falcon and the training dataset. And this introduced a new model. We call it Secure Falcon. And of course, we tested the Secure Falcon with the test dataset, and we do some model fitting. And after that, we have some classification that the code is vulnerable or non-vulnerable. What we want to achieve here, you can imagine, if you're familiar with bounded model checking, that even for simple program, for example, there is a small program with only 20 lines, but a lot of loop iteration, a lot of unwind, then it can take even for a week for ESBMC or any bounded model checker to verify the correctness of the program. However, we want to teach this for an AI to do this with the same things and try to only say the code is vulnerable or not. And basically, of course, we cannot achieve 100% success rate like using formal verification method. However, is it possible to achieve really good results with almost instant time? Basically, you can imagine we can reach 100% success rate with ESBMC, for example, within 10 hours. And the question is, can we reach, for example, 90% accuracy within 1 second? Because if this is the case, then we can immediately remove most of the low-hanging fruit vulnerabilities, and we can remove most of the vulnerabilities from the code immediately. And after that, we can use this trained model to distinguish between vulnerable and non-vulnerable code. And we designed a 12 decode layer. In this, this is not important what kind of variables and hyperparameters we were used, but this was the decoder layer we have used. This is based on the original Falcon architecture, but we use different parameters. And we use the S attention layer. We use many different layers in order to try to classify the code is vulnerable or not. And surprisingly, the Secure Falcon achieved 94% of accuracy And it means if we give a code, for example, for Form AI dataset to Secure Falcon, immediately the inference time is immediate. So within 1 second, less than 1 second, immediately can say that the code is vulnerable or not. So basically, of course, we cannot achieve 100% like with ESBMC, but 94% is quite okay. And we can see the benefits that we can immediately say that the code is vulnerable or not with 94% of accuracy. So basically, just this is conclude my presentation. I go back to the beginning of the presentation and I show again this very important challenges. So basically, the first challenge was to create a large data set. The second one is to make some vulnerability detection and get a deep arithmetic understanding of large language model. And to avoid false positive and false negatives, of course, we label the dataset using bounded model checkers. They are, of course, up to bound K. They are not introducing false positive results because we have a counterexamples, of course. And all of these challenges, we tried also to teach for an AI to make some machine learning techniques. And it has turned out that using some techniques, we are able to teach a machine what ESBMC is doing. Of course, we cannot with 100% success rate because formal verification method is based on match and it's correct always. But with 94% of accuracy, we can classify the code that is vulnerable or non-vulnerable. And of course, we can also check it with the test data set. These data set never seen by the model in the training process. And of course, the success rate was on this data set with 94%. So basically, we have created a data set. After the data set, we try to repair the code based on some large language model. And also we try to teach an existing model in case Falcon LLM, because it's free of charge and can be downloaded from, for example, from Hugging Face. Okay, thank you very much. And I'm stopped my sharing, but if you have any question, just let me know. And of course, you can also write me an email and we can have some discussion on the topic.
Okay, thanks a lot, Norbert, for the presentation. I don't know if you recall, but at the beginning of the presentation, I said this would be an intriguing presentation about LLMs and software security, because yeah, I was quite intrigued by how we're gonna use the LLMs into that specific area. But right now, for me at least, it feels quite clear the importance, the limitations, and the possibilities with not only LLMs but AI in general for software security through formal verification. This is not I mean, our audience here is quite broad in terms of background, so I wouldn't say everybody here has the you know, knows every term in formal verification or software security, but it was quite clear what exactly you are achieving with this. We have a first question here from Patricia. She asked you to comment about the challenges that you've mentioned before, and one of them, the hallucination one. Quite an interesting word.
Yeah, in AI, the hallucination is if you check, for example, there are many research scientists that use this word hallucination when, for example, if you have tried GPT or many different large language models. I don't want to give an example in source code analysis because it's much harder to explain and imagine. But you can imagine, for example, that please, if you ask, for example, GPT, please tell me name 5 city or 10 city that start with letter A. It should be a simple task because letter A, you can check that the city name is starting with letter A. However, if you try with, for example, also with GPT, sometimes there is a chance that, for example, GPTs give you a result that it's not starting with A, but totally different, a different letter. This means hallucination because the model, if you go to the web page and try it right now, you have such kind of results. This is called hallucination because the model thinks that he really give you only city names that is starting with letter A. However, this is not the case. And also it can happen in software engineering, in software security, when the model says that this software there is no bug, there is no security issue with this program. However, there is. So basically, this is important that sometimes we cannot believe what is the output of the AI.
Yeah. About this hallucination topic, I've noticed that you've created the whole data set using the GPT 3.5, which, if I'm not mistaken, is an LLM that's trained over a very broad range of tokens. Like it has a lot of different subjects in it. So would it be less hallucinating, for instance, if you would create your own LLM, for instance, out of a lemma model that's trained on a very specific code base from GitHub, for instance. So instead of training, using a very big corpora, just a very specific corporate software C code.
Yeah. Yeah, basically, this is one of the aim that, for example, if we know that some code base is secure and there is not too much problem with this code base, then we can try to start training the AI, and the AI going to generate more secure codes. So basically, yes, this is a really good approach. That, for example, if you know that you have some really secure code that you have written or your students written or something like that, then you can start the training on that code because you know that these are much more secure than that you can find on GitHub. So this is a good approach. If you give some secure codes to the AI, then the AI going to also learn this pattern and try to make also secure code. Yeah.
Yes, or even just changing the GP3 prompt to, request code that's secure as well. Maybe that's might decrease a little bit the percentage of unsecure code that it generates.
Yeah.
Another, yeah, go ahead.
Yeah. Basically, this is really important to understand what's the difference between these secure codes and non-secure code. And basically, for example, this secure Falcon what we have created, it can also be used to create new secure codes, and we can also start training on the AI on that.
Interesting, very interesting. Another question here from Alison, Steve. Um, Yeah, do you see ChatGPT or other tools being used to generate secure code uh, rather than just code snippets or code suggestions?
You mean that let's me in a short time, do you see children or other tools being used to generate secure reward code or just? Yeah, basically it depends on the size of the token. So basically, I think a few days ago, GPT also announced the 128K tokens. It means you can input 300 pages, for example, in the prompt. So basically, right now, it means you can create a really large code set. Of course, we are not here, and if somebody asks me that who should write my secure code, an AI or a human being, right now, I'm choose the human being, so don't worry. But maybe in the near future, who knows? Every piece of code will be written by AI, and right now this is a small step. Right now we can write some small function. You can create some Python codes, C codes, and many different codes. However, if we increase the token size, then we can create more complex codes. So basically, in the near future, I see that these kind of models will be used to generate more complex codes. And right now,
Hmm.
of course, everybody is using to create some code snippets in order to please give me this prime factorization, give me this sorting algorithm, and so on and so on. But later on, we can use it to create a whole project. Right now, it's of
Yeah.
course there are a lot of limitations.
Hmm. And people are using these code snippets on the industry right now without ever thinking about these possible uh, insecurities. Um, Um, yeah. So one very interesting application that you mentioned was the ability to heal the code. You know, you provide the code sample and you ask for GPT to correct the code based on an external tool, which is the I forgot the name, the SMBC, something like that.
Yes, BFC. Yeah. Yeah.
And that's a very interesting thing because you can interactively, like in a cascading scheme, to improve the code step by step, right? But my question is, at the end of this process, the code that you have, is that equal to the code that you presented initially in terms of the outputs, in terms of what it's going to produce?
Um, Basically, it's also a challenging question. So if you spot, for example, we have an original code and we have a modified code. This is an NP-hard problem in mathematics to check that the two program is equivalent. So basically, you can imagine, for example, you have a complex code, for example, 1000 line, and some tool says that there is vulnerability in the code. And we ask the LLM or the AI, please try to fix this code. And for example, the new code is print hello world, and there is no vulnerability in the new code, of course, but the new code and the original one is totally different. So basically, yes, this is a really challenging problem how to solve this, and this is a future research direction that we have to solve.
Okay. Another question from Patricia is, are there any works involving LLMs and formal requirements specifications?
You mean that yeah, so basically, I have seen some papers and also some ongoing research that they try to use not exactly for the software, but for formal requirements, for example, for a hardware module, what the hardware should do, and they check that the specification of the hardware is correct or not. Of course, I'm not an expert on this field, that how to check that the hardware module is really doing the things that they need to do, but there are also ongoing research that's it's much faster to use AI to check these formal requirements than a human being. Of course, we also have to check what is the accuracy, because right now I can imagine that still the human being is better in this field. But in the near future, like in a table game like chess or something like that, AI is much better. It's in the last 20 years. So maybe in the next 5 years, there is no question that AI will be much better programmer than us.
Yeah, so you mentioned that uh, for the code base you generated using LLM, you had roughly 50% of insecure code that was generated. And you mentioned that this is because it was trained under human created code, which is also insecure sometimes. Do you have like an estimation or a comparison between how many times a human code is insecure versus how many times AI generated code is insecure as well?
There are some comparison, but this is need exactly check because basically using bounded model checker tools or any static analyzer tools or any different tools to check that the code is vulnerable or not. Of course, maybe there is some, we cannot find every vulnerability using this one. To find every vulnerability, we need to use human beings. Of course, this is really time consuming. You can imagine we have 100,000 generated C code, and if I want to check all of the C code by hand that is really vulnerable or not, it's a really long process. So basically, it's also challenging how to check that the code is really vulnerable or not, because of course we rely on some mathematical proofs that there is also some problem that this proof is based on up to some bound. So basically, we cannot be 100% sure that there is no other vulnerability. I just want to
Mhm.
just for a minute share for you my screen. Just 1 minute.
Yes, go
Maybe
ahead.
it's much better to you. You see, my GPT give me 10 city names begins with letter D, with letter A. There is no hallucination. That it's every letter is A, and I tried with the same. Give me 10 city names begins with letter E, and you can see. It's it's basically I don't know how to come up with these city names, but it's definitely not starting with E. When you start with, for example, with the same question, there was no hallucination, and also with this one there was no hallucination, and with some E there was some problem, and you can see that all of the cities are not starting with E. So basically, this we call in AI. This means hallucination. That the AI really thinks that certainly here are 10 city names that begin with the letter E. Of course, this is not true. Of course, I can try it once again, and maybe the answer is good. Yeah, the second one is good, but you can see there was some hallucination. And of course, right now, I can check the answer is correct or not. But you can imagine that, for example, I don't know the answer, and I believe what the AI is telling me. And if I believe that this all of the city name starts with E, then it's a problem. So this is called hallucination. And also this one in here, and also in software security, if a code is say that, oh, this is a vulnerable code, that's not a vulnerable code, then it can be a problem. So this is just an example of what we call hallucination in AI, and it can be happen also for software security. That this piece of code is non-vulnerable, however, it's totally vulnerable. I just wanted to demonstrate that even the newest GPT can hallucinate that, yes, I give you a lot of city names that start with E, and it's totally not. Of course, because I know the answer, I can verify it. But if you don't know the answer, then it's really hard.
Yes, my previous question was a bit like this as well, because and also on the same topic that Walber just asked, if the LLMs are generating some kind of security vulnerability more often, probably than humans, for instance, or the LLM vulnerability generation often happens more often than what human beings generates.
Yes, right now it seems that GPT models generate much more often buffer overflow on scanf. If you are using C or C++, scanf can be a dangerous function if you don't know how to use it properly. And it seems that GPT is really like to do some buffer overflow on scanf. So when I ask you to generate for me a code, most of the cases it generate insecure code on scanf. The reason is you can find on the internet also secure code and non-secure code. So the reason is that just picked up this pattern, but the exact answer is unknown. Just generating, of course. If we want to avoid it and we train on new data, then it can be enhanced and it can be avoid these kind of vulnerabilities. But yeah, most of the cases when there is some user input from terminal in C code and using scanf, GPT is generating insecure code.
Okay, I don't think we have any other questions for you today. Again, thank you very, very much to give this talk. It was very, it cleared a lot of my questions throughout the presentation as well. And yeah, thank you very much to be with us today, Norbert.
Thank you very much. And I think you also have my email. You can share with the group. And if they have any question or later on we need to make some brainstorming, then why not?
Nice. Okay. I'm gonna ask Steve to share your email with the group later today. And yes, thank you very much.
Thank you very much. Thank you very much, guys. See you.
Yes, have a nice night. Bom, pessoal, eu gostaria de agradecer aqui novamente a presença de todos vocês, né? As perguntas também foram muito boas. Agradecer também ao professor Tihanyi por falar com a gente sobre esse tema que está tão em voga, né? Que é o uso de LLM, e como ele tem afetado, né? Essa parte de segurança também. é interessante porque não só do ponto de vista prático, em que as pessoas têm usado bastante LLMs e cada vez mais gerando essas vulnerabilidades, né, por simplesmente confiar cegamente no que o LLM traz como saída, mas é interessante também do ponto de vista de pesquisa, em como a gente pode de fato usar esse tipo de modelo, que tem esses problemas de alucinação, por exemplo, para de fato ajudar e melhorar a segurança das aplicações. Então, aquele exemplo que ele deu de iterativamente ir melhorando o programa a partir de um input externo, né, que é do programa verificador, é bastante interessante e é uma coisa que me pareceu que vai ter que tem bastante aplicabilidade na indústria, né? É, é possível gerar um impacto muito grande com esse tipo de sistema. Tá? Então, eu vou pedir para o Steve depois compartilhar talvez o e-mail dele, caso vocês tenham alguma outra dúvida que queiram direcionar diretamente a ele. E é isso. Novamente, aí, muito obrigado a todos e tenham um excelente dia.